do the bill work. Still doing SAT problems. They're just conceptual. They make you think critically, apply a little bit of math to it. Pretty simple stuff. So this one, it says Townsend Realty purchased Glenview Street property and received a 40% discount off the original price, along with an additional 20% off of the discounted price for purchasing the property in cash. So basically, if you can sum that up, we're going to pay 60% of the original listing price. And then because we're paying cash, we get an additional 20% off of that 60%. Okay, or off of that 40%, the extra discount. This one's a little tough because conventionalism would just say, okay, if I multiply this by 1.6, then I would get the correct answer. But in this case, it's two different levels of discounts. They're not just off of the original price. Okay, and it says, which of the following best approximates the original price in dollars of the Glenview Street property? If we go back to our data, you can see we paid $140,000, right? So what we want to do and what we're trying to figure out is the original price that it was listed at. So I'm going to call that X, right? And our first discount was 40%. 40%, which means that we are paying 60% of whatever X is. So we can express this as 0.6x. And then we get an additional 20%. So that means we have to pay 80% of this 0.6x. So if we set that up, it'll look like that, 0.8 times 0.6x. And this is how we arrived at the $140,000 that we paid. So first thing, we're going to multiply these, 0.8 times 0.6. 0.48. That's still going to be X. Still set equal to 140,000. Then if we divide both sides by 0.48, hit my calculator with this because I can't do that one in my head. 140,000 divided by 0.48. Gives you 29166.67. Okay, so there's 3 sixes. $291,666 is the original purchase price. So off of our answer choices, which one is closer to that? That would be $291,700, or answer choice B is going to be the correct one for this problem. So pretty simple, just hard conceptually, because you got to realize that even though we get that 40% discount, we're still paying 60% of the total purchase price. And then we're only paying 80% of that discounted price again to get us down to 140,000. All right. So today what you have on tap, while we're lecturing, we're going to be talking about imaginary units, okay, and complex numbers. First, we'll go through the 5-minute check and go from there. So our first one of the 5-minute check, it says use the related graph of 0 is equal to x squared minus 4 to determine its solutions. So not a very difficult question. We're just analyzing where we cross the x-axis, because that is what we're looking for solutions, roots, zeros, or x-intercepts. So origins right here. If I go 2 units to the left, I have a cross, so -2 is 1. If I go 2 units to the right from the origin, I get, so 2 and -2 are our roots or zeros. Everybody good? Yeah. All right. The next one, use the related graph of -x squared minus 2x plus 3 to determine its solutions. Once again, we're just analyzing the graph. So starting at the origin, go 1 unit right, we cross right there. So 1 is a solution. Starting at the origin, we go 1, 2, 3 to the left. So our roots or zeros is going to correspond to answer choice A for -3 and 1. Okay, this one we actually have to do a little bit more work. So we're solving, yeah. So we're solving -2x squared plus 5x is equal to 0. Okay, this one, we got to build it up with our graph. So with all parabolas, remember that to find the axis of symmetry or the x value of our coordinates, we use the formula -b over 2a. This one, we just have a +0 at the end of it. So -b, remember that's our linear term, the coefficient that's associated with the single x value, over 2 times the coefficient of our quadratic term, which in this case, it's -2. So -5 over a -2 times 2 is equal to a +5/4 right there. That is the x value of our vertex. So that's 1.25 as a decimal. And I'll just build my table. Okay, here I'll use 1 and 0. 2 and 3, that should get me there. Okay, easiest one to plug in is first we got to find out where our min or maximum value is. That's the y value of our vertex. So we take this 1.25 and we plug it in. So -2 times the quantity of 1.25 squared plus 5 times 1.25. This one, got to use a calculator. 1.25 squared is 1.6 and times 2. That gets me, oh, come on. That gets me to 3.125. And 5 times 1. That's negative 3.125 minus 6.25. So that right there's my vertex. Okay, easy points to plug in are 0. So 0 squared is 0 times -2, which is still 0 plus 0. Going to be right there. So at this point, I'm not actually going to finish building the table. I found one of my zeros. I know its location. It's 1.25 units away. So if I were to take 1.25 units and go in the opposite direction, I'd be at 2.5, right? 1.25 plus 1.25 gives you 2.5. Right there is going to be my other zero. Okay, that's the joy of having the axis of symmetry, because you can minimize your work, not having to plug it all in. Since I found that zero, it's pretty safe to say that 2.5 is the other zero. And looking at my answer choices, that falls between, or that falls for answer B, because 2.5 is between 2 and 3. So even though it's a lot of work to get me there, it's a pretty simple, easy question. Also, looking at this one, since it passes through the origin, we know that our constant at the end of our quadratic equation is always our y-intercept, right? When we plug in 0. In this case, there was no constant, so that has to be 0. 0, 0 is definitely a 0, and then finding my axis of symmetry allows me to map it over very quickly and easily, not having to do a whole lot of redundant work. This one, we're just going to think logically. It says use a quadratic equation to find two real numbers that have a sum of 5 and a product of -14. So sum, remember, that means they're adding up. Product means that they are being multiplied. So two numbers that would multiply to equal a negative 14 add up to equal a positive 5. The two numbers that I think of off the top of my head are 7 and negative 2. 7 times negative 2 is negative 14. 7 plus negative 2 brings you to 5. So this would be answer choice C. And then the last one, a little bit of vocabulary here. Which term is not another name for a solution to the quadratic equation? So remember, solutions are all talking about x-intercepts. They are also referred to as zeros, and they are also referred to as roots. So the only one that does not equal the solution is the vertex. Vertex is probably the most important point when you're graphing these parabolas, but most tests and most everything else, they're going to be concerned about the roots or the x-intercepts. All right. So we've simplified square roots before. Okay, now we're going to perform operations with pure imaginary numbers, and we're going to perform operations with complex numbers. Okay, the first definition term is imaginary unit. The imaginary unit is always expressed as I. Okay, as an I. It looks kind of like a backward J. What this represents is that I is equal to the square root of a negative 1. Okay, I is the square root of negative 1. I know what you're thinking. Hey, you can't have a negative square. And in fact, you would be right. There is no real number that you can square it to equal a negative number. That's because two negatives multiplied by each other equal a positive, and two positives multiplied by each other equal a positive, right? This is purely imaginary, okay? Also builds up on complex numbers. So if I is the square root of negative 1, that would mean that I squared is equal to negative 1. Okay, and if we expand on this, so we have I squared, what if we cubed it? Okay, well, we have I, then we have negative 1 once we multiply it. We multiply it by itself again, we get a negative I. Okay, because you're taking negative 1 times I, which gives you negative I. Then the final one in this pattern is I to the 4th. I to the 4th is similar to I squared times I squared. So negative 1 times negative 1 is going to bring you to 1. Okay. So what this is, it's a pattern. Okay, it's always going to repeat itself. Right? And there's different stages. So knowing this, if I went to I to the 5th power, it would be 1 times I, which would just give me I. Okay? I to the 6th power is the same thing as taking I squared times itself 3 times. You could actually break it down like that if you wanted to. I squared times I squared times I squared. We know that I squared is negative 1, so negative 1 times negative 1 times negative 1. Negative 1 times negative 1 is 1, times negative 1 gives you negative 1 again. Okay, I to the 7th power. Taking a negative 1 times I again gives you negative I. Okay, and then I to the 8th power. Okay, it's like taking negative 1 times negative 1 times negative 1 times negative 1, which is going to bring you back to 1. This is handy and it's helpful Because let's say if I wanted to figure out what I to the 53rd power would be. Yep, I to the 53rd power. Okay, so if I think about that, and you can see it's a cycle of 4 spots, right? It's either going to be I, -1, -I, or 1. What I can do is I can divide this exponent by 4. Okay, 53 divided by 4, if you were to punch that into a calculator, you would get 13.25. Okay, what this says, or what this means, is that it's completed this whole cycle 13 times, right? And then the 0.25 means that we're on the next, or we're on the first part of the cycle. So I to the 53rd power is just going to be I, because that's the first portion of the cycle, how it repeats itself. If you divide it and you get a 0.5, okay, that means you're at the second stage of the cycle. If you divide it and you get 0.75, you're at the third stage of the cycle. Okay, if you divide it and you get a whole number, it means you just completed the cycle and you're at the fourth stage. And then it goes right back to 0.25, which brings you back up here. 0.5, 0.75, whole number. 2.5, 5, 0.75, whole number. And it repeats itself. It never stops. It never quits. So I to the 60th power is 15. 60 divided by 4 is 15. It's going to be 1. Okay, so you have to simplify them a little bit like that. You should all have at least this pattern down. Yeah, I'll give you a couple seconds to write that down. It's also shown in the book if you prefer to do it that way. It is shown on page 172 at the bottom. Okay, it runs through the first versions of the cycle. What's up? Your pencil broke? Should have some mechanical pencils back there, buddy. All right. Good to go? Perfect. This marker writes great, but it doesn't erase. Just means I can't make mistakes today. It'll take me an hour to erase it. Okay, so that is the imaginary unit. Where this comes into play is dealing with parabolas that have no real solutions. So it would be like a parabola with the vertex above the x-axis with it opening up. So it never truly touches the x-axis. It has imaginary roots. That's why we express it as no real solutions. It's not that it doesn't have solutions, it's just that they're not real. The next one is a pure imaginary number. Okay, and then you have a complex number. A complex number is broken down into 2 parts. Okay, and I'm just using variables. It's A plus or minus BI. Okay, A is what's known as the real part. That's a real number. BI, B is just a variable for the coefficient. It could be any number. This is your imaginary part. Okay, it's complex because it has a real portion and an imaginary portion. A pure imaginary number is just expressed as BI. It'll be 6I or 7I or 8I. Okay. Okay, the complex conjugate. Okay, that comes into when we're dealing with division. More or less, a complex conjugate is a complex number that has a different arithmetic in the middle. So if this is a plus bi, the complex conjugate to that would be a minus bi. Okay, these two in itself are complex conjugates. When they're multiplied against each other, you are actually going to be left with a whole real number. Okay, that's the purpose of the complex conjugate. It's used in division. So you will see that here shortly. All right. So portions of this section are going to ask you to solve square roots that have negative numbers. Okay, in order to do this, what we need to realize is that you have a product property of radicals. Product property of radicals states that the square root of a term AB can be broken down into the square root of A times the square root of B. Okay, it allows you to split numbers. This because we're looking for exact numbers. Okay, we don't want decimals when we're doing this. Okay, it's kind of like when we were doing the trig stuff and we expanded them and then took the square root and put them back together. We're doing that same thing, except for one of these numbers is going to be -1, which corresponds to I, right? The square root of -1. So in the case of trying to simplify the square root of a -28, I want to think of a perfect square. So like 1, 4, 9, 16, 25, that can be multiplied into 28. Okay, in this case, it would be 4, right? 7 times 4 is 28. So this -28, we're going to break it down into the square root of 4 times the square root of 7 times the square root of -1. Okay, as we just learned, square root of -1, we can simplify that now to I. Right? The square root of 7, we can't do anything with that. Okay, it's not a perfect square. 7 is prime. So nothing else multiplies into it except for 1 and 7. So the square root of 7 has to stay. Okay, the square root of 4 is 2. Okay, so the square root of -28, they want us to simplify it, it's going to be 2i times the square root of 7. So you can see that we're using this property to break it apart, simplify our perfect squares where we can get them, take care of our -1, and we would list our number like that. Okay, that's the simplest, most exact answer we can get. Can we plug the square root of 7 into a calculator? Yes, we can. But it's not a rational number. It'll be a decimal that never ends or repeats itself. Okay, so it's not the most exact answer. Whereas 2i times the square root of 7 is. So they can break it down into -1 times 4 times 7. Okay, split them all into their square roots. We get I times 2, or 2i times the square root of 7. And that would be our final answer. Okay, realize that this is multiplication. It's just it's just the common format that it's 2i times the square root of 7. It could be 2 square root of 7i, could be the square root of 7 times 2i. They're multiplication, so it's all means the same thing. Just this is the accepted format. Okay, 2i times the square root of 7. On the next one. Okay, once again, I want to find the biggest square that'll get multiplied into 32. right? So knowing that, I know that 16 times 2 is equal to 32. So 16 is the biggest square that gets multiplied evenly. So to simplify it, the square root of negative 32 gets broken down into the square root of 2 times the square root of 16 times the square root of negative 1. Okay? 2 is not a perfect square. Okay, it's not a rational number, so I can't do anything with that. That has to stay, the square root of 2. Square root of 16 is 4. The square root of negative 1 is I. So the most exact answer that I could put the negative square root of 32, or square root of negative 32, excuse me, simplified is 4i times the square root of 2. And once again, I break it all apart. I simplify the square roots of my perfect squares, and then I leave whatever radical cannot be simplified. So you can see square root of negative 1, that's going to be our I. So 4i times the square root of 2. Again, it's pretty simple. It's just splitting them all apart and then putting them back together. Honestly, the hardest part of that is trying to figure out your perfect squares that multiply evenly into it. Okay, but we've gone over perfect squares. Like you have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100, all the way up. Okay, so this one, simplify negative 50. Thinking about it, the perfect square that multiplies into it is 25. So we break it apart into its pieces. That's the square root of 2. That won't change. Times the square root of 25, which will break down to 5. Times the square root of negative 1, which is I. So this answer is 5i times the square root of 2. Okay, once again, splitting it apart, simplifying the perfect squares when we get them, and then putting it all back together. Okay, simplify the square root of negative 45. Perfect square that goes into it is 9, right? 9 times 5 is 45. So that would be split down into the square root of 9 times the square root of 5 times the square root of negative 1, which would leave you with 3i times the square root of 5. Okay, and it's just the same process. Whenever we're taking care of these, we break them apart, simplify, and then put them back together. Okay, the next thing that we're going to be doing after simplifying square roots of negative numbers is you're going to be carrying out arithmetic operations on pure imaginary numbers and complex numbers. Okay, when it's pure imaginary, it's pretty simple. All you're doing is just multiplying those across. We just have to remember that I squared is negative 1. So in other words, wherever we see a negative 1 or an I squared, it's going to flip the sign. So in this case, we'd have negative 3i times 2i. Okay, negative 3 times 2 gives you a negative 6. I times I gives you I squared. Okay, I squared is equal to a negative 1. So this is really negative 6 times negative 1, which flips the sign, and your simplified answer will be a real number of 6. Okay. So the important thing is we got to remember that I squared is -1. So in other words, it changes the sign, right? Just like that. Okay, pure imaginary numbers are pretty simple. Ooh, jerks. Ugh. All right. So square root of -12 times the square root of -2. Okay, first thing I'm going to do is I'm going to simplify them first. Okay, by splitting them apart and putting them back together. So -2, that's broken down into the square root of 2 times the square root of -1. That's the square root of 2i, or I square root of 2. This one here gets broken down into the square root of 3 times the square root of 4 times the square root -1. So that is going to be 2i times the square root of 3. And multiplying those together is going to give me 2i squared times the square root of 6. Okay, this I squared gets simplified to a -1. So that would be -2 square root of 6. At least that's what it should be. See if I'm right. They do it just a little bit different than the way I did it. I simplified it first. So, but you end up with the same answer. So you can see they take the square root of -12 and the square root of -2. They broke it apart into -1 and the square root of 12. That's where the I comes from. Then they multiplied them, get -1 times the square root of 24. But then they have to split this apart again. So as -1 times the square root of 4, which is 2, times the square root of 6. Okay, so you can see there's two different ways. We can break it apart and simplify them and then multiply it, or we can multiply it and then break it apart and simplify. But regardless, either way, we both still have to break it apart and simplify. Okay, this one, multiplying pure imaginary numbers. So 3 times 5 is 15. I times I is I squared. I squared is equal to a -1. -1 times 15 gives you -15. Okay, so you multiply the coefficients to get 15, multiply your imaginary units to get I squared. And when it's all said and done, we're ending up with a -15. Okay, like I said, pure imaginary numbers, those are pretty simple to handle. This one here, so we could break it into, I'll do that one for you guys because these are the harder ones. So we have the square root of -2 times the square root of -6. Okay, I'm going to multiply them, or I'm going to break them apart first. So I get I square root of 2, because the square root of -1, times I times the square root of 6. Multiply those to get I squared square root of 12. Okay, I squared is going to be -1. Square root of 12 can be broken down into the square root of 3 times the square root of 4. So this would be -2 square root of 3. The negative comes from I squared because it's -1. The 2 comes from the square root of 4. And then square root of 3 we can't touch because it is already simplified down. Awesome. All right. Here, we're solving for y. Okay. This, we'd solve it just like we'd solve any other equation. Okay, but we're given 5y squared plus 20 is equal to 0. So just thinking about this, we know we're going to end up with a negative square root, right? Because we're going to subtract 20, we're going to divide it by 5. So 5y squared plus 20 is equal to 0, and we're trying to solve for y. So we handle it the same exact process as we do to solve. Subtract 20 from both sides. We have 5y squared is equal to a negative 20. And we divide both sides by 5. Okay, continuing to isolate the variable. Your y squared is equal to a negative 4. Okay, and the way we get rid of the square is we have to take the square root of both sides. So y is equal to the square root of negative 4. Negative 4 can be broken, or the square root of negative 4 can be broken down to the square root of 4 times the square root of negative 1. Square root of 4 is 2. Square root of negative 1 is I. So our final answer is 2i. Okay, just isolating the variable like you know how to do. Doesn't change anything. It's just we're adding that now once we hit a negative, oh, hang on. I got to go plus or minus. Because I use the square root sign. We're just adding in the possibility of taking the negative square root or the square root of a negative number. So the original equation, we subtract 20 from both sides to isolate the variable. We divide each side by 5. We take the square root. Okay, that's where the plus or minus comes from. Then it's broken down because negative 4 can be broken into the square root of 4 times the square root of negative 1. So our final answer is plus or minus 2i. All right, got another one. So we're dealing with 2x squared plus 50. And that is equal to 0. Isolate the variable again, so we subtract 50 on both sides. To be left with 2x squared is equal to a negative 50. Okay, then we divide both sides by 2. We get x squared is equal to a negative 25. We take the square root of both sides, so that x is equal to plus or minus the square root of negative 25. Square root of 25 is 5. And the square root of negative 1 is I. So our final answer is plus or minus 5i. Okay, you can see it's a pretty simple process because it's repeating the same thing over and over again. It really doesn't get too tricky until you're dealing with division and multiplication. Okay, so here are your complex numbers. Okay, complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. A is called the real part and b is called the imaginary part. Okay, and we're going to do arithmetic operations with these complex numbers. Okay, we're going to add them, we're going to subtract them, we're going to multiply them, and we're going to divide them. The good news is most of this stuff you've previously done. Like multiplying is all based upon FOIL. Addition and subtraction is all about combining like terms. Division involves FOIL, but we have to use the complex conjugate. Okay, and that gets a little tricky, but you'll see that. Oh. Okay, so find the values of x and y that make the equation true. What we're going to do here is first, we want to match our real parts and set them equal to each other. Okay, so my real part here is 2x. Real part is -14. So 2 and x have to multiply together to be -14. And my imaginary part on the first equation is yi. The imaginary part on the second equation is a -3i. So we're going to set the coefficients equal to each other. And then we're going to solve for our variables. So our real part is 2x is equal to a -14. Okay, and now we want to solve for x. So we divide by 2 on both sides. And we're left that x is equal to a -7. Okay, the imaginary parts in this equation are very easy. It's y set equal to the imaginary part of the second equation, which is -3. Okay, we didn't have to solve that one because once we set them equal, they stay. You can see on the imaginary part, we don't bring over the i's. Okay, because for them to be equal, we need to match coefficients. Okay, so we're matching coefficients. So set the real parts equal to each other and the imaginary parts equal to each other, talking about coefficients. Okay, then they solve for x. Then they set the imaginary parts equal to each other. This one didn't need to be solved. So for this answer, x is equal to a -7, y is equal to a -3. If we were to plug those in for our variables, we'd end up with -14 minus 3i to make them equal to each other. Okay, so find the values of x and y that make the equation 3x minus yi equal to 15 plus 2i true. So this one's actually a little bit of a trick question because we have a -y. So we end up having to divide by -1, just changes the sign. So once again, we set our real parts together. So 3x is equal to 15. We divide by 3 on both sides to get that x is equal to 5. Okay, this next one, -y, is equal to 2. So just understand that there is a coefficient of 1 in front of that. You can't have a -y, so we have to divide by -1 on both sides, which yields y is equal to -2. All right, here we actually get to it. Okay, so first parts we're going to talk about is addition and subtraction. Addition and subtraction can be broken down into 3 words. Combine like terms. So whenever we're adding or subtracting, you want to combine like terms. Okay, the same way that you can't add x squared and x. They're not like terms. In this case, we have our imaginary unit, right, which can be combined with other imaginary units, and then we have the real units, which can be combined with other real portions. Okay, so the problem we're working with is 3 plus 5i as a quantity plus 2 minus 4i. I. Okay. So my real portions, 3 and 2 can be combined. My imaginary portions, 5 and -4 can be combined. Whoa. So what's 3 plus 2? That's an easy one. 3 plus 2 is 5. That's our imaginary, that's our real portion. What's 5 plus a -4? Well, that's going to be 1 as a positive. So the answer to this one, after we combine like terms, is 5 plus I. Okay, combining like terms for addition and subtraction. So you can see here, they have 3 plus 2 is the real portion, 5 minus 4, or 5 plus a -4, however you want to look at it, as your imaginary portion. Once you carry out that arithmetic, you're left with 5 plus I. I'll talk too much today. My voice is a little hoarse. It's been so long since I've lectured. Okay, the tougher ones of addition and subtraction is subtraction. Okay, that's because it's hard to, it can be difficult to keep track of the signs. All right, so we have 4 minus 6i as a quantity, subtracted 3 minus 7i as a quantity. Okay, the positives are pretty easy. What's 4 minus 3? Well, that's 1. Right? What's a -6 minus a -7? So we're subtracting a negative, so it's really we're adding it. So -6 plus 7 gives you a positive 1, and the complex number that would be resulting is 1 plus I. Once again, addition and subtraction, it's broken down into combining like terms. Okay, 4 minus 3 gives you 1, -6 plus 7 gives you I. Hardest part about subtraction is keep track of where the signs are. Okay, you can switch your subtraction to addition and adjust the signs on each one of these if that suits your bill. But that's where you got to be detailed. Okay, it's not terribly difficult. You just got to be detailed with it, or you're still just combining like terms. So here we have a real portion of 2 and 3, and it's addition. So what's 2 plus 3? That's 5. In the process of an elimination or deductive reasoning, however you want to look at it, we only have one answer choice with 5. So we know it should be answer D. But if we look at the imaginary portion, 6i plus 4i gives you 10i. Okay, combining like terms for addition and subtraction. Okay, 3 minus a -2. So since we're minusing a negative, it's really addition. So 3 plus 2 is 5. 2i minus 5i gives you a -3i. Okay, you can see it's pretty simple. All right, so multiplying. When you're multiplying, you want to think of FOIL. Okay, first terms, outside terms, inside terms, last terms. Or in other words, say it's a plus bi times a plus bi. These are your first terms. These are your outside terms. These are your inside terms. These are your last terms. You got to multiply them across, doing the distributive property twice. Okay, multiplying with FOIL, you'll be ending up with a complex number unless they are complex conjugates of each other. Okay, this one, it's still imaginary numbers. It says in an AC circuit, the voltage E, current I, and impedance Z are related by the formula E equals I times Z. So find the voltage in a circuit with a current of 1 plus 4 I amps and impedance of 3 minus 6 I amps. So we're taking these two terms, 1 plus 4I times 3 minus 6I. And we want to use FOIL. So my first terms, 1 times 3 gives me 3. My outside terms, 1 times a negative 6I gives me a negative 6I. Okay, 4I times 3 gives me a positive 12I. 4I times a negative 6I gives me negative 24I squared. Okay, remember I squared is equal to a negative 1. So this is really negative 24 times negative 1, which gives you a positive 24. Once you simplify I squared, we can combine our like terms. Okay, 3 and 24 combine to make 27. Negative 6I and 12I combine to make a positive 6I. Okay, and then we write it in the proper complex number format with the real numbers out front and the imaginary numbers in back. The key here for multiplication, do not forget to simplify I squared. It's negative 1. It adjusts the sign of whatever coefficient it is associated with. So if it's with a negative 24, that now becomes 24. If it's with a positive 36, now that becomes a negative 36. Because I squared is equivalent to negative 1. Okay, so they plug it all in. 1 times 3, 1 times negative 6I, 4I times 3, 4I times negative 6I. That's your FOIL process. That's what you get resulting. Okay, they combine their like terms, and then they take care of the I squared, which is negative 1. So you can see once you've done that, you can combine like terms. For multiplication, we should never end up with multiple units of I. Okay, there's only one imaginary piece because you end up with I squared, and that turns it into a real number. Okay, here we have the next one. So we're doing the same formula. We're going to multiply 1 minus 3I times 3 plus 2I. So still using FOIL as we come through. So 1 minus 3I times 3 plus 2I. Okay, 1 times 3 gives me 3. 1 times positive 2I gives me a positive 2I. Negative 3I times 3 gives me a negative 9I. Negative 3I times a positive 2I is negative 6I squared. I squared is equal to a negative 1. So this, instead of being a negative 6, it's really a positive 6. Okay, 2I and negative 9I are going to combine to be a negative 7I. 3 plus 6 leaves me with 9. So my final answer is 9 minus 7I. Once again, the trick is make sure that you simplify I squared into negative 1. Other than that, it aligns pretty well with what you've already done. Okay, here's where it gets a little complex. Okay, whenever you're dividing, we still use the FOIL process, but we need to do that with the complex conjugate of the denominator, okay, or the bottom term. So divide, still FOIL, but underneath that is the complex conjugate of the denominator or the divisor. So if it's written something like this one's easy because it has a denominator. If it's written like that, where it's going left to right, it's the complex conjugate of this term. Okay? This is 3 plus 2i. Complex conjugate of 3 plus 2i is 3 minus 2i. Okay, and once we multiply that through using FOIL, you end up with a whole number or a real number in the denominator. Okay, there is no imaginary unit once we're done, except for in the numerator. Okay, so the question we have is 5i divided by 3 plus 2i, and we're multiplying that by the complex conjugate, which would be 3 minus 2i for both the numerator and the denominator. Okay, this one's pretty simple because the numerator is just the distributive property. 5i times 3 gives me 15i. 5i times a negative 2i gives me a negative 10i squared. Okay, simplify negative 1. So that would be 10 plus 15i. Okay, because it's negative 10, I squared is negative 1. And then we always put the real portion out front. Okay, for the denominator, we have to use FOIL. But since these are complex conjugates, like I said, the imaginary unit will disappear. So 3 times 3 is 9. 3 times negative 2i is negative 6i. 2i times 3 is a positive 6i. So you can see those two are going to cancel out. And then 2i times a negative 2i is negative 4i squared. Okay, combine your like terms and take care of the negative 1. So really that's going to break down to 9 plus 4, because it's negative 4i squared. So that's negative 1. So our denominator here is going to be 13. Okay, so we'd write our answer as 10 plus 15i over 13. Okay, but what they want you to do is they want you to split this into a whole real term. So it'll be 10 thirteenths plus 15 thirteenths I. Okay, so you can see once you're multiplying with complex conjugate in the denominator, we're left with a whole real number. Okay, there should be no element of I in the denominator once we're done. Okay, it all gets broken out and simplified that way. So they multiply it. Okay, I squared, remember, turns into negative 1. Okay. And then they break it into a plus bi form. So that is your final answer. Okay, here's a situation that actually makes it pretty simple. Okay, here you can see we have a pure imaginary number in the denominator. In this case, what we need to multiply by is I divided by I. We'll multiply it by 1. Okay, and that'll simplify our answer because 5i or 2i doesn't have a complex conjugate. It has to be a complex number to have a complex conjugate. So it's purely imaginary. So we have 5 plus I, perfect, over 2I. And we're going to multiply that by I over I. Okay, and all that is to get rid of the imaginary unit in the denominator. So the denominator is going to turn into 2I squared, or -2. The numerator, 5 times I, gives you 5I. I times I, positive plus I squared. So I, I squared simplifies to a -1. So that's -1 plus 5I. Write it into our form as 1/2, because -1 divided by -2 makes it positive, plus, minus. So 1/2 minus 5/2 I would be our final answer here. Pretty sure that's right. Yeah. Because, like I said, because this one's pure imaginary, not complex, it doesn't have a complex conjugate. So we just multiply by I over I. Okay, so we get 5I plus I squared. I squared is -1. So that's what switches the sign in the denominator. And then because we broke it apart and we have a negative over a negative, that's why we have a positive 1/2. And then minus 5/2 I. All right, pretty sure this is the last one. So here we multiply by the complex conjugate again, which will be 1 minus I. We'd be left with 3/2 plus 3/2 I. All righty, folks. That's what I have for you. That's your lecture.